Good afternoon, everyone. We hope you're all excited for this session. We hope you're happy and healthy. And thank you all for joining and welcome to the session on machine learning for CAE Simulation. So let me first start off by introducing ourselves because I know we have familiar faces in the audience, but I'm pretty sure there are also many who do not know us yet. So my name is Melissa, and I will be your host for today. And the session will take around an hour, so if you have any questions during that time, you can ask those in the Q&A section, which should be on the right side of your screen. My colleague Saeid, he will present the technology today, so I will make sure he will get all your questions, either at the end of the session if there's time, or otherwise we will get in touch with you. And you can see our emails on the screen, so you can get in touch with us as well. In general, I would encourage you to stay till the end because we have a special benchmark offer. So definitely stay. Saeid and I both work for In Summa Innovation. We are the exclusive reseller for MSC Software in the BeNeLux, that's Belgium, Netherlands, and Luxembourg. And we offer computer-aided engineering simulation software. We help all kinds of companies here with research and development projects, designing products, prototypes, etc. But today we will not focus on MSC software, but instead on a different kind of technology. Saeid will introduce you to machine learning for CAE simulation. So today we will only show you some of the endless possibilities, just the tip of the iceberg if you like. If you want more in detail technical info, feel free to contact us. Links are on the screen. So why machine learning? It's quite unusual, it's fairly new and an unknown topic. And when you think of CAE, you would not really think of using machine learning with it. So why? Saeid will show you today that with machine learning, engineers can first of all save a lot of time. We can reduce runtime for new parameters and go from hours to literally seconds. Second, you can also increase accuracy. And overall, you can engineer much more efficiently. In other words, it's what we believe will be the future for CAE. So with that said, I'd like to hand it over to Saeid. Saeid, you can show us in detail. If you could please share your screen and take it away for us.
Thank you very much, Melissa. Yeah, let me share my screen. Okay. Thank you very much, all of you, to joining today's webinar. We are going to discuss about machine learning, as Melissa said, for CAE simulation. Let's start with a simple example. A nonlinear material rubber joint is a typical classical mechanical engineering simulation. Here you can see the animation is produced by machine learning. So what we are interested to see is the displacement at extremity of joint. We call it Y1. With 15 runs from simulation with 3 important parameters like mass, X1, and money-revealing parameter, X2 and X3. So we can see here the results. Solid line are from machine learning and dashed line is from simulation. You can see how fit they are to each other and predicting the maximum. The important point is here for FEM, we need 21 minutes for each simulation, but with Lunar, which is a machine learning software, takes 1 second. So we save time here and we have accuracy. This is all about this presentation. Today, first, I'm going to have an introduction about machine learning. After that, I will introduce Adiza Lunar, which is a machine learning platform. After, I will present you some case studies, including CFD, finite element, multi-body dynamics, and multi-physics. And after that, I will show you the platform. So let's define a few words. What is machine learning? Machine learning is a study of computer algorithms that improve automatically through experience. For machine learning, we use neural network. So what is neural network? You can see at the right side a picture of neural network. Neural network is a computational learning system that uses a network of functions to understand and translate the data input of one form into a desired output. We can see here we have an input layer or parameter, like for simulation. You have a hidden layer, which is the relation between parameter, weights, and other things. And we have an output layer, which is the desired output we want to see. So why combining the machine learning and simulation? Both machine learning and simulation have the same goal. Both of them want to predict the behavior of a system with data analysis and mathematical modeling. Simulation data can fit machine learning as a training data. At the same time, machine learning can help simulation, and we can have a hybrid method going toward autonomous simulation. At the right side, you can see vertical axis and horizontal axis here. As an engineer, we are interested in physics. We have a physics-based model. At the same time, for machine learning and data science, they have a black box of neural networks. So what the interest region for us is here, physics-guided neural network. With this one, we get advantage of neural network and help simulation to be faster and more accurate. Let's start with this simple example. Imagine you want to model this lake. So we know that as an engineer or simulation engineer, modeling such a case with many parameters is very difficult and takes too much time because we have many parameters here. Imagine we have an inflow boundary condition. We want to know there is ice in the lake or not. What is the overflow? What is the outflow? What is the mixing at the bottom of a lake? How much is solar radiation? Is raining day? We have snow or not? And all of these parameters make simulation much difficult and time consuming. So because of that, and we want to drive temperature in each point of this lake, and we know that, okay, which day of the year we are. So if we complete this simulation, maybe we can do 3, 4, but if you want to change every parameter, it takes too much time. If you want to predict water temperature, the input drivers, I listed 11 of them here. You can see day of the year, depths, air temperature, wind speed, rain, is it freezing or not, is it snowing or not, and other parameters. This input driver, we can use them to construct the physics-based loss function, which means that we know already the relation between density and temperature. We know the relation between depth and density. And we have many equations in fluid mechanics and physics for relation between them. Like this one is the empirical equation between density and temperature. And based on that, we can build our neural network. We fit with the input parameters, and we use a weight function and relation between parameters. At the end, we can predict the water temperature. And this is all about we want to explain to make everything smarter and faster. We believe that machine learning will greatly impact the product development process because we avoid long, complex, and costly simulation process. Simulation can provide training data for machine learning, and we replace the costly analysis process, and we can go toward autonomous system. We can see here for every classical simulation, we have a 3-step from CAD model, preparing the geometry, meshing, and after that we are going to model setting, put inflow, boundary condition, and all of the setting needed for a model, a setting for all of the PD equation we want to solve. And after that, we are going to solver, and we have a running time here, and we have a post-processing, and all of this stage takes time. With machine learning, we want to get rid of this stage. If we have some simulation files, we can get rid of this stage, and we just care about variable x at input and response y. And this make it everything faster and will help us to create the autonomous system for simulation. Here we can see some classical and also new methods to use for optimization and other studies like parametric studies, trial and error. We need sometimes 10 run for that. For post design, for optimization and model fitting, sometimes in 100 runs. And for certification, if you want to have reliability studies, maybe in 1,000 runs. So all of these steps require numerous solver runs. After this introduction, let me introduce this platform today. This is a Lunar. This is a powerful portfolio, is including 3 different software, Lunar, COSAR, and Nova. This platform actually is a CAE-centric innovation platform and apply modern machine learning, artificial intelligence, and reduce order modeling, and also design optimization. In this presentation, I'm going to talk about Lunar. Lunar is especially for simulation and uses past experience we had output, past result of simulation to predict new responses for reduce order modeling. And this is help out a lot if you are working on some cases already and we have maybe 1,000 simulations. So we can use those data already you have to predict the new results if you want to change some parameters. So what is model reduction? Imagine we have a parameter matrix X as the input. For all of simulation, we have some input and we have response at the end Y. So first we are going to use decomposition method to decompose the matrix we have as input and output. And after that, we will have a model reduction for our PDEs. From this stage, there is a different methods to doing that. After that, we reconstruct the system again. Some of the methods you are familiar with that, like RBF or Kriging or other methods for interpolation and prediction. From this stage, when we reconstruct our system using machine learning algorithms, after that, we give a new parameter X. We had some parameter here, X as the input, but here we want to give a new parameter and predict the new response. From this stage, we can maybe 1 second just enter the new parameter, and in 1 second, you have the response for that. Step 1, as I said, is decomposition and classification. There is a lot of different methods for that, like SVD, singular value decomposition, or Fourier transform, clustering, or deep learning, a convolutional neural network, and data fusion. So we use one of these methods, depends the case we have. And step 2 is a prediction, sometimes in interpolation, like grading method or radial basis function, polynomial regression. And we're using this method at the end, we have a space, we have like, by a space, I mean the variable you have, based on time, the change at the time response of your system you have, and you can predict the new result. Let's see this example. The problem is that we have a function x and t, and we have response y from simulation. Some data we have in simulation, and we have some response in simulation. We want to find if you have a new parameter, what is the response? So we need to design a space always to say that how many simulation we have. Green dots here, green circles here are known data from simulation. And red dots here are unknown data. We give some new parameter like x new, and we want to find out how much is the y, the response of system to these new parameters. And we are doing that easily by defining sample x and y. We have it already from simulation. And we want to know using these decomposition methods and Lunar system to predict how much is the new magnitude and time response to the system. So what is the advantage using Lunar? We start with a simple design of experiment. We define sample X and compute Y. In every software we have it, some sample of X, and we can compute Y at the result. So we can design or a space with the few Y selected sampling, like this one, 4 or 5 sample from a simulation. We have a time response from simulation, and after that we can drive the other magnitude we want. So it's important to design your DOE very well, and you can reach adaptive learning and system learn and improve as you learn and make it more autonomous. And the advantage is that we have a real-time computing. By pressing one button, you have the result. And these methods, most of them are highly accurate, and we have precision for that. And we can do a physical domain decomposition and not just fitting. Not we are not talking about some fitting method or other things. We are just using the domain decomposition, and we can produce 3D animations. And all of this process have a low memory. We need a low memory, low CPU, and low storage for all of this process. You can do that in your laptop. And what is the workflow for Lunar? So if you want, imagine you have some result from simulation, how you can do that. So Lunar working based on CSV file. In every software, you can export CSV file. So you have an input parameter, such as here, we have a cylinder, we have a pressure load here. The parameter could be mass, diameter, length, material properties, and other physical properties. We give them as a matrix variable set A to set N. To Lunar. At the same time, we have some result from simulation that will be input Y file for Lunar. We have n time responses, such as in a fluid mechanic case, you give inflow and you have velocity in every point of your system. From this stage, Lunar, we give some given new parameters, new set of variables, and we want to see the reaction of the system to these new parameters, and we use the model reduction. And after that, Lunar predicts the new result as a YN file. So the set is based on CSV file. So we can use all of the software, engineering software, to export this file and use Lunar to predict the new result. Let's talk about some case studies. In this part, I will present a few CFD cases and multi-physics cases, and after that, multi-body dynamic case. And we can see what is the advantage of using Lunar. Here is a steady state analysis doing by STFlow software. So we want to predict the flow rate of a fan by changing the shape of that. We know that here we have a fan with 5,000 RPM. We use a steady AAL equation to solve it. So for fan, we know that number of wings, short diameter, fan diameter, and bus diameter are important to predict the flow rate of a fan. So if you want to model all of these parameters, every single geometry going to have a different number of wings and different fan diameter takes too much time. So because of that, we define this parameter number of wings here with a minimum 3, maximum 10, and other parameter like this with a minimum and maximum. We had the 30 sample cases from simulation, and we give these cases to a software to predict the new result for us. And the objective function for us is outflow mass based on kilogram per second. Here we can see the predicted results by simulation, and this is a Lunar. How we can see there is a minor difference with less than 1%. And calculation time here is for STFlow with 72 cores, takes 60 minutes to calculate each case. And for the Lunar takes only a few seconds. And this is one of the advantages using that. You save a lot of time here to use machine learning instead of classical simulation. Another case is transient analysis, actually thermal transient analysis. We want to predict the maximum temperature of the IC chip. We can see here the system we want to model for CFD simulation. Here is a board. We have an IC chip here as a heat source, and we have a thermal conductive rubber, and we have a box around that. So we use a natural convection to model that. We need a space around that to model natural convection. And from simulation, we drive the temperature contour. We have a temperature at every point of the board and the IC and other part of that. So for this one, we want to predict the maximum temperature if we want to change some parameters. Here we use 3 parameters here. Rubber size, rubber thermal conductivity, and IC chip high heat generation startup time. So these parameters are most important parameter to change the maximum temperature. And we define minimum and maximum for all of these parameters. And we have here also two curve for a startup time, because reduced startup time could reduce the heat generation. But by shortening the startup time, we can do that. And we can see the result here. These are the prediction by Lunar. The dashed line and solid line you can see here is very difficult even to detect them. They are very fit together and they can predict the maximum temperature very well. The solid lines are from CS stream for simulation, and here the dashed line are from machine learning case. So we can see the precision here, and more important is about timing. For a system, each of these cases take 1 minute with 72 cores, and with Lunar, with just your laptop, usually normal laptop you are using, is 1 second. And this is only is running time, so you need to pre-processing, post-processing, and other details. But here, only with the change of parameter, you can derive the new results. Let's go another example. We know that in CFD and simulation, aerodynamic cases usually takes a lot of time. We want to predict of aerodynamic sound analysis. Here we have a simple cylinder here, 3D case, and we have inflow here and outflow here. We want to drive sound pressure level based on frequency, and the parameter, we put only one parameter, inflow velocity, with different velocities from 5 meters per second to 15 meters per second. So with this change of parameters, we want to see the effect on the sound pressure level. Here are the results. Dashed line is from Ciflo CFD software, and solid line is Lunar. We can see the trend of both data is very close to each other. And about here, about 99.5% is the precision of the method. And most important part here is that for a CFD case, initial turbulent flow field when you are using LES method with current number 5 takes 3 hours and 50 minutes with 72 cores. For sound analysis, takes 4 hours and 40 minutes with 72 cores. And for post-processing, 1 minute per data. Totally, these two steps are 8 hours and 30 minutes with 72 cores. But for Lunar prediction, we have a few seconds. With these two cases, we spent more than around 70 hours, but for Lunar takes only 2 or 3 seconds. And this is one of the important things for the case, especially when we need to spend much time for running. Let's go for another example, but this one is multi-physics interaction. We have a fluid and we have solid, this kind of FSI simulation. We have a pump membrane here. We have an inlet velocity and outlet velocity, and the middle of that is a membrane. From simulation, we want to know what is the displacement at the center of the membrane. Data is derived from simulation here. You can see the displacement at the center of membrane based on different inlet flow we have from CFD. From simulation, we have 8 cases. We can see here the change of displacement. And we want to optimize the system and know that maybe we want to limit the membrane displacement, and we want to know which velocity giving us this displacement. Here are the results. We have the 8 case. You can see the blue lines here. There are 8 case sample base curve for us, and we want to, with our objective here, to have an inflow velocity 60 point. And doing optimization. For initial optimization case, the minimum stiffness, maximum flow is this curve, and optimized curve, you can see it here. And based on objective, we determine the best curve give us the desired displacement is this one. And we can compare the Lunar result with FE result here, red line and blue line. And this animation is derived by Lunar. You don't need to produce new animation in simulation software, just you are going in Lunar and directly give you new animation based on all data you have. Another case is optimization mass distribution for a given trajectory for a multi-body dynamic case. Here is a car using Adam software. Input here is weight of the driver side, and another one is mass on the passenger side. And based on that, we have the output from simulation is coordinates x, y, z, and yaw, pitch, and roll of a car. And we had a 10 run here with mass 1 from 50 to 100, and mass 2 is 0 to 100. So based on that, we want to see the chassis displacement vertical and chassis displacement roll. We can see here the dashed line and solid lines are from Adams and Lunar. They are very matched together for both parameters. And even you can optimize that. You want to see that you can determine a target. You say that, okay, I want the value to be here and how much will be yaw or other parameter. You can fix some parameter to drive other parameters. So you can do optimization here and based on a target you determine for software. And for Adams cases, we can see here the mass 1 is 80. Prediction of Lunar is 80.3. Mass 2 is 40 and prediction of Lunar is 37.6. This is another example, a very simple example here. We want to drive the displacement at extremity of a joint with the two parameters, force and shore A, x2 and x3. We use 8th run for training the data. At the end, we derive the displacement from Lunar. Time from final element is 15 minutes, but for Lunar is 1 second. Here is another example of ball impact with rupture. We had the 15 runs as a training set for 4 parameters, position x1 and 2, ball speed at impact angle x4. And we are interested at the simulation, we had contact force y1. So we can use this data to predict the new results for final element took 1 minute, Lunar 1 second. Another example here you can see is a test of airbag and using that for optimization. So we have the 3 input parameters, deceleration, braking speed, x1 and x2, and we had the airbag mass debit x3. So the output channel for us is the pressure on the thorax and pelvis acceleration. Both of them, they are output for us. So we have some base curves here, database, you can see the blue lines. And we want to use, we determine a target. We say that, okay, how much pressure we want at this point of thorax compression and other things. And based on that, drive the input parameters. We can do call it kind of inverse optimization. So here is initial VS target, and here you can see the optimized case by Lunar give you the desired input parameters. So here is kind of give you an overview about machine learning and Lunar, and now I'm going to show you a real case with the Lunar. Here are the Lunar GUI. It look like this. We can define a project here. And after that, we can give 3 CSV file, as I told you, one of them as an input. One of them is a result file from simulation. Another one is new parameter we are interested to know, and also for validation of the case. After that, simply you load your files in Lunar and choose your type of solver you want, different ROM methods. And after that, you can do interpolation and drive. Actually, this is kind of the name, interpolation or prediction, is the different algorithm. And you can do a sensitivity analysis and drive the parameter effects on your system. And after, you can do optimization, inverse analysis, and you can define the target curve and find optimal parameters, and you can produce animation. So here I'm going to solve this simple case. It's a parametric system. It's a box beam compression. We have a 2 model here. We have a 2 model parameter as an input, thickness and density x1 and x2. And output for us from simulation was contact force y1 and displacement y2. We want to predict in real-time results and animation for various parameter and values. So let's go Lunar. This is the interface of Lunar. Here we can define a project. First, let me show you. The case we have is here. We such as this X input file based on thickness and density of material. We had the 6 training case from simulation. We determined them, and we have the result for these parameters. And we have for this one, we have a Y file, is a CSV file. We had it from simulation for 6 cases. So we use this data to predict the new results. And here we have, after this, we have 3 new parameters. We want to know that, okay, we don't have simulation for them. We want to have the result for them. And we have the simulation files here. We had the 6 run, and all of simulation files are here. And we want to use them to predict the new results. So let's start. First, we define a project. Maybe just call it beam simply. And here define the folder you want to work on that. We select here. So, okay. So we define the folder. So we are going to upload parameter X. Here we added. This parameter actually is a parameter input for the simulations, like as I mentioned, is the thickness here and density. And the Y file. And validation file xn is a new parameter. We want to see how the system predict the results. You can even have a time axis, but I ignore it at the moment. So we press load files. So we can see these curves for 6 training sets from simulation. We have the result, final element result of them. We gave X and we have Y. This curve are from simulation. And now we just press this button, interpolation, to have a new parameters. So for those 3 parameters were unknown for us. Now we have the result of that. So, and we want to make sure how accurate these 3 parameters are. We just simply import the results from final element to just be sure this curve are working. Just import curve. We have this file from simulation. We added 3 files for 3 new parameters. And we can see difference of them here, solid line and dashed lines. Solid lines are from Lunar and dashed lines are from finite element. And this is based on that, we can say that, okay, how accurate is our prediction? Of course, more training data provide more accurate results. And it depends on the type of solver we choose. Here we have a different type of solver, pod, clustering, kriging, RBF, ARBF, and other methods. And all of them, they have a different settings, subsettings here. You can use pod for pod RBF, pod, kriging, and other methods here. So we have these results. So we can see the effect of different parameters on the results. Here we have a thickness and density. We can see here the most important parameter here is the thickness has more effect on the result than density. And also you can define a new range here, work on your DOE. There are several types here. You can work on data and see that have exact statistics, how much all of this data affect your results. So let's have one of these curves. Just isolate it, this curve from simulation, and just hide the base curve we had from data. So let's have two new parameters. So we have the current simulation, we had some parameter. We can have some new parameters, like for thickness, we can put 1.5 and produce a new result. We can do that 2.5 for new thickness and put it here, and we can run it. So for the new parameter, based on the previous parameters, so we can see the new results here. And this we had this curve, and now we have these two new curves from the new parameters. So you don't need to come back to your simulation to produce the new results. So you can produce your result here directly in Lunar. And even you can generate the range of data. We will come back to this later. So we said about yn. So we had the three validation case. We can see the magnitudes here, and we can compare them together from finite element and from Lunar. And we have model context, and Lunar can derive how many modes you have in your curve and your responses. And we can see here clearly mode 1 has more effect on the result, and then the blue one is mode 2, and we can ignore other modes. For parameter 2 almost is the same, but still green and blue has mode 3, and mode 4 has a little effect on that, but other modes can be ignored. And we want, of course, to see animation, how we can produce animation. We have animation tab here. We can go for configuration. We give a directory that where are our file. I put them on desktop in this folder. Here our simulation file. I select this folder. And give the extension for animation file. And press OK. And now we just press animation to run animation. Okay, you can see animation almost in a second is produced. And you can run your animation, the new parameter here, maybe less FPS. Yeah, and this is what we are talking about. You don't need to come back to the software you produce your results. It doesn't matter, be a finite element software or multi-body dynamics. You can produce your animation here with the new parameter directly. You can define new parameters and drive the new animations. So that's make everything easier. And there is optimization methods here. I'm not going to talk about them today, but there is many optimization methods. And we have here, we talk about the different solvers. Different solver could affect the result you have. And you can do something here to know that, how you know that which, let me to clean this again and clear those data we produced. And show all curves. Okay, we had this from Lunar, and you want to know that if you choose different method, like we have part here, if you choose clustering and do interpolation, you have a different results. So it's important to know how to choose these methods to have a more accurate result. Here you can run a simple script here to compare different methods. And you will have a report here and give you, if you use different method, how accurate is the result are for different sample validation case 1, 2, 3. And based on this validation curve, and this is why we call it validation curve. Based on this validation curve, you choose your method, which method is more accurate for you. And after that, you enter the new parameter and you will have a new results. So here we had the three validation case. Validation case 1, we can see, okay, if you are RBF Gaussian, you are the 86% accurate, or other methods, you can see a percentage of that. And validation case 2, and validation case 3, we had the 3 validation case. And based on that, give you which method is more accurate. And you can use this report to choose which method is working better with the data you have. For sensitivity analysis, actually, if you are just going isolate this curve and hide it again, we can see the parameter effects gradient of a parameter here. See that, okay, how much the local effect of the parameter on all data, and even we can generate range here. Imagine we choose curve 3 and just reset values and use thickness or material density, and we can produce a range like this one is kind of a population study and give you a corridor. In this corridor, those parameter, like here we have thickness and density of material. You can create a corridor with the thickness 2, which with this constant rho, with thickness is working much better, and create a corridor for your design. You can see here, we just fixed the row here and we created 100 samples here. And this create kind of corridor. Maybe you can make it 1,000 and give you some design corridor to be to your design. Just all a parameter go inside this corridor. And other parameters here, you can do a linear regression, and also is a gradient. You show the gradient of your variables you have. And you can do a lot of settings for your animation, and all of them, how you want to your line be look like, and other details you are interested. You can clear all of things you have produced. You can go back to base cases again and show all curves and close everything. And for animation also, you can go with this tab. You have animation here. You can have a different like other software. You can have points. You can have a different looks of that, different axis view. And this case I presented to you is the most simple case, and showing that we can do everything here and we don't need to go back to simulation software. If we did the CFD simulation or FEM simulation, multi-body dynamic simulation, if you have some good samples, we don't need to always go back to software and doing that. We can stay in Lunar and with a very short time and accurate methods predict the new results. Yeah, and thanks for your attention. So I just try to keep it as simple as possible. And of course, there is a lot of examples. There is more for automobile industry and other industries. Just I try to keep it simple as possible to everyone can follow the presentation. Thank you very much, Melissa. If you
Yes, thank you. Nice demo. I see there's quite a couple of questions. I'm not sure if we have time to go over all of them, but first of all, let me reshare my screen. Yes, so thank you, Saeed. As said before, that's something I would first like to mention before we go to the questions. We can offer you an engineering benchmark. We can, as you've seen in the examples, reduce your runtime from from hours to minutes, maybe even to seconds. So, and we can offer this free with zero effort from your side, because as Saeed said, you probably already have the data laying around you. You do so many simulations as an engineer that you probably already have the data that we need to do a benchmark for this. So that's why we can offer this to you. However, it's limited available. So basically it will be a first come, first serve basis. So that's why I would encourage you to opt in quickly. Now, how do you opt in? You will receive a feedback survey after this with the email you signed up for the session, so you can fill that in. and please give Saeed some feedback on the session. We really appreciate that. And then you can opt in, or you can contact us directly, of course. Again, our links are on the screen. Let me now quickly go to the questions for you, Saeed, because I have a couple.
Yeah.
Sure. In the beginning, you talked about the model, how it works, and decomposition, reduction. So what is physical decomposition is a question. I think it's a good one for you.
What is physical decomposition? Actually, decomposition is a mathematical method. And so we have some metrics, as I explained that. So input metrics like X input parameters, and we have Y responses. And decomposition is that we are going to make our system simpler, like the eigenvalue for a matrix. And we drive the principal, and you can see the principal driver of that matrix, and we call this decomposition method. We have a different type of decomposition, singular value decomposition, and other methods that I presented them.
Hope that clarifies it. I'm not sure who asked the question because they joined anonymous. Next one, what is the advantage of Lunar in comparison to other platforms such as MATLAB Neural Toolbox?
Yeah, it's a good question actually, because in MATLAB and other tools, we have some script, they are doing a special application. But in Lunar, what we are presenting now is that you can is all of the platform simulation. We try to have them in Lunar as producing animation and other details I show you. That's all of the aspects are important for simulation. Lunar is the CAE centric software and is not like to have some codes and some toolbox to help for some software. This is the general software, help every software you are using at the moment, doesn't matter be ANSYS or MSC products or other products. So you can easily bring this simulation down and produce your animation and every aspect of that. In MATLAB, we don't have such a thing. We are just a neural network toolbox, help us for some data we have. But this one is more handy, more easier, and we have a lot of more things. Even we can do inverse optimization. All of these things I presented, maybe you have a code, you can do a kriging, or you can do a pod or something. But all of them here, we have them together in a one software, one GUI, and can work with other softwares easily. That is the advantage of that, and is of course faster.
That's a bigger advantage that is faster. I hope that answers the question. If not, do get in touch with us. So there's another one that I see from someone anonymous. How can I improve the transferability of the machine learning model without increasing? I'm not sure whether there should.
I don't know what's the question. Could you say again? I didn't get the question.
How can you improve the transferability of the machine learning model without increasing?
Yeah, the question is not clear for me still, but I think transferability of machine learning without increasing, I mean, maybe just we need the right training data, training set. Imagine we want to do machine learning, apply machine learning for a simulation case. First, it's very important to have a right training set. Maybe we have 6 runs in simulation, and after that, export this result for Lunar to do a machine learning. So it's important how you are choosing these 6 training sets. If you have more training set, will be much easier because system learn faster. But there is a rule for that. We call that 2n+1. They say that the minimum cases for machine learning, the n is number of parameter. If you have a system with 1 parameter, 2n+1 will be 3 training case minimum. So training case depends. More is much better because system learns. And sometimes if you have a space, DOE range you have, if you cover it with a wise selection, you will have a more accurate result with machine learning.
Yeah, that makes sense. So it could be that one time just 6 is enough, and sometimes you might need more, like maybe 9 or even 12. Or
Exactly. Depends on input parameters. So for some cases, if you have a 10 input parameters, so you need, of course, around 20 training sets. So you want to reach and obtain accurate result. You don't want just produce some result. You can, with 2 cases, you can produce result. But the question is that how accurate they are. So for training sets, it's very important how many parameters you have at the input and how many training set you need to cover and the range of them. As I show in some example, minimum and maximum, you have a range for each parameter. You should cover those range with your training sets to be able, machine learning can predict the right result for you.
yes, I think that's also related to some other questions that are being asked. Because someone asked, how do you know if the machine learning prediction is accurate without running the analysis for comparison? So that
Yeah,
ties in with what you just said, I think.
yeah, actually, that's one actually is very important question. For machine learning, always you have a 2 set of data, input and output we derive from simulation. And as I show you in the demo, we have validation data, such as with 3 parameters we choose. We have the result already in the software, final element or CFD or other software. So we derive that's result. First, we use Lunar to predict that, and we compare that result with final element. After that, we choose our method or solver to create more match result. That is the key point, actually. You should use that to be sure your results are accurate. After that, when you trust the system, a system learn this method with this data is working better, you can give a new parameter and have a new result. So first, you need to have a training set and maybe 3 parameters, test the software, is working very well, is accurate, and give the result you want. And after that, use it for produce the new results and predict the new responses.
Yes. Yeah, it's in a name, right? Machine learning, so it needs to learn from something.
Exactly.
Okay, let me check quickly. There's a couple more questions. I see who the questions are from. Oh, one last one. How much is time saving? That's a good one.
How
Do you
much? It
have?
depends the case. Sometimes
Yes.
actually I had experience for a case for like 4-kilometer pipe or something like that that are running for CFD to 25 days. So I run it for 6 different parameters. If I use that in machine learning, maybe save me 3-4 months at least. So will be
It's a lot
5
of time.
seconds. Yeah, so that is really important. In some, it's not like this too. I want to use machine learning immediately. Sometimes you are working on wind turbine analysis in a company like that. So you have a lot of data for CFD structure and many things. You have those data already. And if when you want to, change a small parameter in your design, such as the diameter or angle or something like that. So you have those data easily in machine learning. You can just use that data to predict the new result you have. And in many industries, we have time-consuming simulations. Sometimes with the 72 cores, it takes 1 month to run a simulation. So because of that, this is a big advantage. Depends what are you doing, what is your case, and what you are interested to know. If you are doing everyday CFD simulation or final element simulation, multi-body dynamic simulation, and for the same cases almost, you just change the parameters. That is important to use machine learning because really save too much time. Hours will be a second.
Yes. Yes, and that's what you say. It's case by case, and that's also, I think, exactly why it's so nice that we can offer a benchmark now, so that we can look at your specific case that you have as an engineer. Because yeah, with some people, maybe in your case, we can save indeed hours instead of minutes. So that's why I
Yeah,
would also
exactly.
highly encourage everyone, because I think we might still do one question. Let me check. Can we use it only with sensor data without any simulation in the beginning?
Use that center data.
Sensor.
Oh, sensor.
So
Yeah, of
sensors, yeah.
course. It's just here we are talking just about the data. We're talking about the data from simulation. If you have a data from experiment analysis or sensor, yeah, of course we can do that.
Yeah.
So it's the same. We're just working with the input X and output Y. So doesn't matter be from simulation or from sensors. So of course, if we from simulation, we can have a new result of animation and other stuff related to simulation. But of course, with the pure data from sensor and experiment, we can do that. Yes.
Yeah, we're of course focusing on CAE simulation for now, but definitely it's machine learning in general. I think I skipped over one that we might still have time to answer, and then I think we should come to a close. So I think I will do this the last one, and then other questions that keep pouring in, we will get in touch with you. So
Yeah, sure.
the example seems limited to one geometry on which several parameters are varied and predicted. Is the method also capable to have the geometry itself as a variable? So predict the impact of a certain dimension.
Yeah, that is a very good question, actually. So because sometimes we change when we are talking about parameters, design parameters, as I present for a fan model, we change the geometry because we add the blade on that, change the diameter of that, change the base diameter, everything. So this is about the from geometry to post-processing is all about that. So easily you can change the geometry as I present that for a fan, and you have a new result. It's not limited to just the boundary condition or something like that. It could be geometry and other parameters.
Yeah, I think that makes it clear. If not, we're happy to answer any more questions.
Please send me email if you have more questions, you need more data, get in touch with us. Yeah.
Yeah, as said, our screens our links are on the screen. Sorry, and you will receive an email very soon from me with the feedback survey, so you can opt in for a personal benchmark, so we can go over your specific case. As I said, it's limited available, but you will find the details in the email. And then all I would like to say, thank you, Saeed. I hope this was a nice introduction to machine learning for everyone. I will send you also the recording of this webinar, but it will probably be tomorrow. And you can still, again, send us a message anytime, get in touch, and then we can answer your questions. So thank you.
Thank you, Lisa.
Yeah, thank you, Saeed. Thank you, everyone, for joining. We hope you stay happy and healthy. We hope to see you sometime soon again at maybe a next webinar, maybe with your personal benchmark, or maybe sometime soon in real life if that's possible again. For now, thank you, and thank you all for joining. And
yeah, thank you.
bye-bye.
Thank you. Have a nice day. Bye-bye.